page 15, and now we're going to review the paired means t-test. What is that? So regardless of whether we're talking about the student test or the Welch test, an independent samples t-test is intended to be used in a situation where you have two samples that are, well, independent of one another. So this situation would arise naturally when your participants are assigned randomly to one of two experimental conditions, but it provides a very poor approximation to other types of research designs. In particular, a repeated measures design in which each participant is measured with respect to the same outcome variable in both of your experimental conditions. So again, in particular, a repeated measures design in which each participant is measured with respect to the same outcome variable in both experimental conditions is not suited for analysis using the independent samples t-test. For example, we might be interested in whether listening to country music reduces people's working memory capacity compared to not listening to that music. To that end, we could measure each person's working memory capacity in two conditions, with the country music and without the music. So in an experimental design such as this one, each participant appears in both groups. This requires us to approach the problem in a different way. So this would mean that we're now going to use our paired samples t-test. So you may also hear this referred to as a paired means t-test or a dependent samples t-test or a dependent means t-test. And as with the other t-tests that we've already reviewed, the outcome variable must be measured on an interval or ratio level scale. So mathematically, a paired means t-test, it's identical to a one sample mean t-test. And again, those were the first tests that we did yesterday. And so again, mathematically, this new test, this paired means t-test, is identical to the one sample mean t-test, with the added first step of computing the difference for each participant. So in terms of your notation, we're going to denote the differences as a capital D or a big D, where the DI is xi1 minus xi2 for each individual in our sample. So for example, if we want to know if the student scored differently on exam 1 and exam 2, and then Becky scored 95 points on exam 1, and then she scored 90 on the second exam, the difference for Becky would be computed as D Becky equals 95 minus 90, which equals 5, which again is your value 1 minus value 2, 95 minus 90. Because the paired means t-test uses the same underlying procedures as with the one sample means t-test, it's not surprising that the assumptions of the paired means t-test are very similar to those that we saw earlier on, with the added requirement of having paired data. Now we're moving to page 16. So with paired samples, the data from your two measurements needs to be matched or paired. And in psychological research, this typically involves taking two means from the same individuals. So for example, you might have a pre-test and a post-test design. The same participants are measured on the same variable before and after the intervention. However, it is also possible to have matched data from different individuals. Examples include like a parent-child pairing or an older sibling, younger sibling pairing. Also with the paired samples t-test, or the paired means t-test, we have the assumption of normality. So in order to use the t-distribution to estimate this sampling distribution, there needs to be evidence that the sampling distribution is normally distributed. The sampling distribution here is the distribution of the differences. The sampling distribution of the differences will be normal if the differences are normally distributed in the population, or if the sample size is sufficiently large. So that sounds the same. Then we're looking at the independence of the pairs. So each pair of observations should be independent of the other pairs. And again, this sounds similar to something we talked about yesterday. This means that the measurement of one pair should not influence the measurement of another pair. And so for this particular paired means t-test, we're going to look at the Dr. Chico's class data set. And so to remind us what's in this set, this data set is where we have the different observations that we recorded. So we have Dr. Chico's class, and in her class, the students are taking 2 major tests, and they're taking one early in the semester, and then they're going to take another test later in the semester. So to hear her tell it, Dr. Chico, she says that she runs a very hard class, one that most students will find to be very challenging. But Dr. Chico, she argues that by setting hard assessments, students are then encouraged to work harder. Her theory, Dr. Chico's theory, is that the first test is a bit of a wake-up call for the majority of her students, and when they realize how hard her class really is, then they tend to work harder when the second test comes around, and they'll get a better mark. So is this correct? So to test this, we're going to use the data from the Chico CSV file, and this data set contains 3 variables. So it has the student ID, the grade on their first test, so grade test 1, and then the grade test 2. So if we look in our descriptive statistics chart, which is on page 16 before we actually run this in JASP, if we look at this spreadsheet, it does seem like the class is a hard one. We can see because the mean is 56.980 on the first test, and the mean on the second test is just a little bit higher. It's 58.385. So on the first test, the lowest grade was 42. The highest grade was 71. On the second test, the lowest grade was a 44, and the highest grade on the second test was a 72. So not much change. So again, these tests, they are both scored out of 100 points, and most grades, again, are between 50 and 60 points. So it does look like there is a slight, very, very slight improvement from test 1 to test 2. And so we will run this in JASP in a moment, but we have figure 9.10, which is on page 16. And this is descriptive statistics for these 2 tests in Dr. Chico's class. If we take a quick look at the descriptive stats, again, we can see this impression seems to be supported. Across all 20 students, the mean grade, again, for the first test is 56.98 points. It does rise to 58.39 points on the second test. Although, given that the standard deviations are 6.6 and 6.4 respectively, it's starting to feel like maybe the improvement isn't very much. So this impression is reinforced when you see the means and the confidence intervals that are going to be plotted on figure 9.11a on page 17. If we were to rely on, wow, yeah, I see that. If we were to rely on this plot alone, we'd be tempted to think that the apparent improvement in student performance is just pure chance, because the two confidence intervals have a lot of overlap, which does suggest that the population mean for test 1 could be the same as the population mean on test 2. Nevertheless, this impression would be wrong, and to see why, we can take a look at the scatter plots of the grades for test 1 against the grades for test 2, which are on page 17 in figure 9.11b. And in this plot, each dot corresponds to the 2 grades for a given student. So the line on this scatter plot represents when the scores on the 2 tests are equal. If their grade for test 1, which is on the x-coordinate, equals their grade for test 2 on the y-coordinate, then the dot falls on the line. Points falling above the line are for the students that performed a little bit better on the second test. Critically, almost all of the data points do fall above the diagonal line, which means that almost all of the students do seem to have improved their grade, if only by a small amount. This suggests that we should be looking at the improvement made by each student from one test to the next and treating that as our raw data or our improvement data. So to do this, we haven't done it yet, but when we do it, we will be creating the new variable for the improvement variable that each student makes. And then we're going to add that to our Chico data set. And the easiest way to do this is to just compute the new variable. To compute the new variable in our software, we can move back to the view of our data set. We'll click on the lower positive button at the rightmost side of our data columns. We will name this variable improvement. We will select the R button, and then after we click the Create Column button, we'll enter the code grade.test2 minus grade.test1. Then we can see our output in figure 9.12, and that will be on page 18. So let's look there. Yep, so we see our code R to compute the improvement scores for the improvement variable. So once we compute this, which we will show soon, so once we have computed this new improvement variable, we can then draw a histogram which shows the distribution of these improvement scores. And again, we'll verify what we get against what is shown in 9.11c. And when we look at this histogram, it is very clear that there is actually real improvement here. The vast majority of the students, they did score higher on the second test than on the first, which is reflected in the fact that almost the entire histogram is above 0. So let's keep going with this concept before we do the statistical input. So again, what is the paired samples t-test? So in light of our previous exploration, we're going to think about now how to construct an appropriate t-test. So one possibility would be to try to run an independent samples t-test using the grade.test1 and grade.test2 as the variables of interest. However, this would clearly be the wrong thing to do, as the independent samples t-test as the independent samples t-test assumes that there is no particular relationship between our two samples. So if we were to try to do the independent samples t-test, then we would be conflating the within subject differences, which is what we're interested in testing, with the between subject variability, which we are not testing. So again, that would be the wrong thing to do, right? We don't want to do the independent samples t-test because that assumes that there is no relationship between the samples. So again, if we were to try to do that independent samples t-test, we would be conflating the within subject differences, which is what we're interested in testing. We'd be conflating the within subject differences with the between subject variability. So the solution to the problem is, instead of running the independent samples t-test on the grade.test1 and grade.test2, we're going to run a one sample t-test on the within subject difference variable of improvement. So to formalize this slightly, if our xi1 is a score for the ith participant obtained in the first variable, and the xi2 is the score that the same person obtained on the second one, then the difference would be di equals xi1 minus xi2. And notice that the difference scores is variable 1 minus variable 2 and not the other way around. So if we want improvement to correspond to a positive value difference, we actually want test 2 to be our variable 1. And so equally, we would say that mu d equals mu1 minus mu2. And that would be the population mean for this variable difference. So to convert this to a hypothesis test, our null hypothesis is that the mean difference is 0, so mu d equals 0, and then the alternative hypothesis is that it is not 0, so mu d does not equal 0. This is assuming we're talking about a two-sided test again, so this is more or less identical to the way we describe the hypotheses for the one sample t-test. The only difference now is that the specific value that the null hypothesis predicts is 0. And so our test statistic is defined in more or less the same way as well. So if we let D denote the mean of the difference, we're now on page 18. So if we let D denote the mean of the difference scores, then the D over the SE sub D, where our standard deviation D is estimated. So the standard deviation subscript D estimation would actually be our standard deviation of our difference scores. So since this is just an ordinary one sample t-test with nothing special going on, the degrees of freedom would be n-1, where n is the number of pairs, and that's it. So the paired samples t-test isn't really a new test at all. It's just a one sample t-test, but it's being applied to the difference between the two variables. So it's actually very simple. Now the only reason it merits this discussion to be as long as it has been is because we've just gone through what you need to be able to recognize when the paired samples t-test is appropriate, and to understand why it's better than the independent samples t-test when the data are paired. So then again, we need to go back and we need to do this in JASP. So how do you do a paired samples t-test in our software? So again, one possibility would be to follow the process that we outlined above, And that would be to create a difference variable and then run the one sample t-test on the difference variable. Since we've already created a variable called improvement, then we can just do that, and then we're going to get the results from figure 9.13. And again, we're showing our results from the one sample t-test on the paired difference scores. And so again, this output is obviously formatted exactly the same way that it was the last time we used the one sample t-test analysis, and it does confirm our intuition. There is an average improvement of 1.4 points from test 1 to test 2, and this is significantly different from the T19 equaling 6.48 with a p-value of less than 0.001. But suppose that you're a lazy statistician or a lazy student and you don't want to go through all that effort of creating that new improvement variable. Perhaps you just want to keep the difference between one sample and a paired samples test clear in your mind. And if you just want to do it that way, you could do it that way as well. So you could go into the JASP paired samples t-test analysis, and as we're just about to see, the numbers would be identical to those that came from the one sample t-test, which of course they have to be given that the paired samples t-test is just a one sample test under the hood. So let's go ahead and we're going to use the paired sample t-test function, and this is going to be for Chico's class. So let's pull that one here. So we're going to open Chico. And here it is. All right, so we opened it and there it is. And now we're going to go under t-test and we're going to do the paired samples t-test. We're going to move our grade 2 and our grade 1 to the variables box in that order. And then our software is going to compute the difference. And then we're going to double check that we have our student t-test selected, and we are doing the two-tailed test, which means that measure 1 does not equal measure 2. That is under your alternative hypothesis. Then we're going to go under additional statistics and we're going to check our location parameter and our 95% confidence interval. And the result should be the exact same output as we saw in 9.14. And again, this is the paired samples t-test, grade test 2 minus grade test 1. And our t-value is correct, 6.475. The degrees of freedom is n-1 or 19. P-value 0.001. Mean difference 1.405. And the SE difference 0.217. Lower bound of the confidence interval 0.951. Upper 1.859. So let's keep going. So comparing the results of the one sample mean t-test and the paired means t-test, we can see that the t-test statistic, degrees of freedom, p-value, mean difference, 95% confidence interval, they're all identical. Because our p-value is less than the standard 0.05 alpha level, we will reject the null hypothesis, concluding that there is evidence of a level of a difference between the students' scores on the first and second tests in Dr. Chico's class. So here's an example of how our results of this test could be communicated. So in a sample of 20 students, we're at the bottom of page 19, in a sample of 20 students, scores were slightly higher on the second test. So M equals 58.4. So we're going to check descriptives to get this mean. So here we go. It's right here. So again, in a sample of 20 students, scores were slightly higher on the second test. M equals 58.4. Standard deviation 6.4 looks good. Go to page 20. Compared to the first test, M equals 57.0, SD equals 6.6. That difference was statistically significant. T19 equals 6.48. P less than 0.001. 95% CI for the difference 0.95, 1.86 looks good. So having established the assumptions and applications of the one sample mean z-test, the one sample mean t-test, two independent means t-test, paired means t-test, it is crucial to understand not only whether there is a statistically significant difference, but it is also important, it is crucial to understand the magnitude of the difference. And this is where this next concept of effect size becomes very important.